Every commercial flight you have ever taken stopped climbing at roughly the same altitude. Around 40,000 feet, the air becomes a paradox, thin enough to save millions in fuel, yet thin enough to kill you in 15 seconds. The reason planes stay in this narrow band comes down to a balance most passengers never think about. Airline pilots spend their careers chasing the most efficient path through the sky. Above 35,000 feet, the air thins out dramatically. That thin air is the key to saving fuel. As density drops, drag falls even faster. The relationship is direct. Drag is proportional to air density times the square of speed. Every time a plane climbs another 1,000 feet within this band, airlines see about a 5% reduction in fuel burn. For a long-haul flight, that adds up to thousands of dollars saved, multiplied by every trip, every day. But there is a sweet spot. Most modern jets cruise at Mach 0.78, which is just below the point where drag from compressibility starts to rise sharply. At these speeds and altitudes, the engines and wings work together at their most efficient. The plane cuts through less air, but still generates enough lift to stay aloft, and enough thrust to keep moving forward. If a pilot could keep climbing forever, the savings would seem endless. But each step higher brings diminishing returns. The air gets so thin that the benefits start to flatten out. Eventually, the quest for efficiency runs into limits set by physics, not just economics. The perfect altitude is not chosen at random. It is the point where fuel savings, aerodynamic performance, and engine capability all intersect. That is why, for most flights, the cruise level hovers somewhere between 35,000 and 40,000 feet. Above 40,000 feet, the rules of flight start to change. The air thins so much that engines and wings both approach their limits. For the engine, the problem is oxygen. Jet engines rely on a steady flow of dense air to burn fuel and produce thrust. As altitude increases, the air's density drops, and by 40,000 feet, it is less than a quarter of what it is at sea level. That means every second the engine takes in far less mass, and the power it can generate falls sharply. Modern engines use digital controls called FADEC to manage this. FADEC systems automatically cap the thrust as the air thins, preventing the engine from running too hot or approaching a stall inside the compressor. On most airliners, these limits are set so that, even on a hot day, the engine can still produce enough thrust for safe flight, but not much more. The wings face a different challenge. Lift depends on both speed and air density. To keep flying as the air gets thinner, the aircraft must go faster or fly at a higher angle of attack. But as the angle increases, the wing edges closer to stall. At the same time, the maximum safe speed drops because of the risk of shock waves forming on the wing. This narrowing gap between minimum and maximum speeds is why manufacturers define a service ceiling, usually just above 40,000 feet for most commercial jets. At that point, the gains from climbing higher disappear, and the risk of losing control grows. Engineers design these limits into every modern airliner, making sure there is always enough margin for safety, even as the aircraft cruises near the edge of what is physically possible. At high altitude, the safe speed range for a jet can shrink to just a handful of knots. This is the Coffin Corner, the point where the minimum speed to avoid stalling rises, while the maximum speed before hitting Mach limits falls. For an Airbus A320 at 38,000 feet and full weight, that gap can be as little as 4 knots. Fly just a touch too slow and the wings lose lift. Nudge the speed higher and the airflow over the wing goes supersonic, risking loss of control. Pilots must hold the aircraft steady between these converging boundaries, with almost no room for error. In that corner, even a small gust or a slight climb can push the plane outside its limits. At this altitude, every knot matters. Inside the cabin, safety depends on more than just the strength of the fuselage. At 40,000 feet, the outside air pressure is so low that even a small leak can cause the cabin to depressurize in seconds. Regulations require that the cabin altitude never exceeds 8,000 feet during normal flight, preserving enough oxygen for everyone to breathe comfortably. If pressurization fails at cruising altitude, the clock starts ticking. Above 50,000 feet, time of useful consciousness drops to about 15 seconds, barely enough for crew and passengers to don oxygen masks. That is why jets are designed to descend quickly in an emergency. The FAA requires airliners to reach a safe altitude, usually 10,000 feet, in just a few minutes. This balance between cabin pressure, structural limits, and human physiology draws a hard line in the sky, ensuring that passenger survival always comes first. Some aircraft are built to reach far above the usual airline ceiling. Concorde, the most famous example, cruised at 60,000 feet, well into the stratosphere, while carrying passengers at twice the speed of sound. Achieving this required slender delta wings, advanced materials, and engines with afterburners, all designed for thin air and extreme speeds. Today's high-end business jets, like the Gulfstream G650, can fly as high as 51,000 feet. These jets rely on powerful engines, lightweight structures, and sophisticated pressurization systems to keep passengers comfortable at altitudes where the outside air is nearly unbreathable. Each of these high-flying machines is a product of specialized engineering, showing that routine airline altitudes are not about lack of ambition, but about the balance of safety, efficiency, and practicality. Airliners level off where safety and efficiency still hold. Above 40,000 feet, physics draws the line. Every flight today respects that boundary. Proof that limits, not ambition, keep us moving forward.